Hey, it's Adam here. In the first semester of organic chemistry, you were exposed to NMR and IR spectroscopy, and now we're going to introduce mass spectroscopy. What you see here is an example of a mass spectrum, and we're going to go over this in some pretty high level, just looking at this image, and then we're going to go do some PowerPoints, and then come back to this to try to reinforce what we just talked about. What's shown here on the y-axis, this is the relative intensity. The units often is a voltage, but what's presented here is a percent of the intensity. So the largest peak is given an intensity of 100%. So everything else is relative to that large peak. The axis is m over z. And m is the mass of the ion, and z is the charge on the ion. And that's all I'm going to say about that for right now. This spectrum is a known compound. This is bromobenzene. So what we're looking at is bromobenzene, and bromobenzene has a molecular weight of 157.01 grams per mole. Okay, now what I want to do is I want to zoom in at this upper end of the spectrum. And what you can see is that, okay, and I put in some numbers here just to make this a little easier. This is 155. So this large peak is 156, and this is then 157, 158, and 159. And so these slides come from our textbook. I'm going to try to shrink this window a little bit. There we go. And what I'm focusing on here is chapter 14 from Organic Chemistry, David Klein, on mass spectrometry. So mass spectrometry is primarily used to determine the molar mass and formula for a compound. In the mass spectrometry experiment, a compound is vaporized, and then it's ionized, and then it undergoes fragmentation. And the masses of the ions, and that can be the ionized compound, as well as those fragments, those masses are detected and graphed. So that's what we just looked at in the spectrum of bromobenzene. In the process, the spectrum we looked at was a EI spectrum, and in our text, it refers to it as electron impact. I want to let you know that terminology is largely being replaced with electron ionization. In a very simple way, you can think of it as an electron colliding with the molecule. It's probably a little more complex than that, but a sample is vaporized in a chamber that is at high vacuum or very low pressure. So there are very few atmospheric molecules for a molecule to bump into. And when that vaporized molecule is bombarded with a beam of high energy electrons, usually an electron is ejected from the molecule. So if you look at this structure of ethane, beam of electrons bombards the molecule, a single electron is kicked off. So that removes a negative charge. So now we have a radical cation. So it has an odd number of electrons. That makes it a radical. and it's a cation because it carries a +1 charge because it's lost the electron. Now, the mass of the radical cation is the same as the parent compound. So the mass of this radical cation of ethane is the same as the mass of ethane, because the mass of an electron is negligible. The electron's mass is roughly 1 over 2,000 times that of a proton. So, which is roughly 0.05% of the mass of a proton. So it's not that there's no mass, it's just that the mass is negligible. It doesn't amount to anything relative to what we're looking at. Now, if our radical cation was stable and didn't undergo further fragmentation, its mass would be the same as the parent compound, and this is known as the molecular ion, the parent ion. It has a mass equal to the molecule's mass, and this symbol shows a radical cation. More commonly, the plus symbol as the cation will be shown, and the radical is not always shown. Now, what happens more often, though, is that the radical cation, the parent ion, fragments into a radical and a cation. So here you have a methyl radical and the methyl carbocation. Because they carry a charge, they can be deflected by a magnetic field. When a charge is moving, it can be deflected by a magnetic field, and their mass to charge ratio can be separated, and the ions can be directed to a detector sequentially by scanning the field strength and record them. It's important to notice here that neutral charge fragments are not detected. So in this example, the mass spectrum here shows the relative abundance of each of the cations that's formed. And the tallest peak here, the one that's scaled to 100%, is known as the base peak. The base peak is not the same as the molecular ion. It's possible that the molecular ion would be the tallest peak. It's more common that a mass below the molecular ion is the base peak, that some fragment is more abundant than the radical cation unfragmented. In the case of methane, the base peak is the parent ion. So that's at a molecular weight nominally of 16. That's carbon is 12 plus 4 for the protons gives us 16. So in this example, the base peak is the molecular ion. That wasn't the case with our bromobenzene spectrum that I began with. So peaks that have a mass to charge ratio that's less than the molecular ion represent some type of fragment. So in this example, the molecular ion of methane with an M over Z. Z is 1, M is 16, so M over Z is 16. If the radical proton is ejected, then the cation will be decreased by nominally by 1. So this is M over Z equals 15, and this is what we saw in the bromobenzene spectrum. So the subsequent hydrogens can be removed as radicals to give additional peaks that are at masses sequentially 1 less than 15, so 14, 13, and 12. Let me go back a slide, and you can see that. So here's the molecular ion at 16 loss of a radical hydrogen takes us to 15. Loss of another radical proton takes us to 14, 13, and 12. And then there are no other ions possible in the case of methane. So coming back to the example that I started with, bromobenzene, the molecular weight is 157. Now, what I had said earlier is bromobenzene is going to be C6H5Br. Sorry for my shaky hand here. What you may recall is that bromine has two, well, let's see. If I go to a general chemistry textbook, bromine has a mass of 79.0. And you may recall from general chemistry that the masses that we use represent average masses that are based on the natural abundance of the different isotopes of the atoms. There are some atoms that don't have any isotopes. There are many atoms that have isotopes that are present at a very low abundance. But bromine is interesting in that the two isotopes that are, 78.92 and 80.92 are roughly 50-50 in their abundance. So sorry, I got that wrong when I wrote that down. Bromine's average molecular weight is 79.90, and the two isotopes are 78.92 and 80.92. So mass spectrometry is a very important technique and continues to grow in importance because of the power of mass spectroscopy. It's widely used in the pharmaceutical industry for drug discovery and the study of drug metabolism, reaction monitoring, and as the cost of instrumentation comes down, it's more common even to see mass spectrometry used in routine quality control assays. Biotechnology uses mass spectrometry very heavily for sequencing protein. Clinical applications, particularly with small volume samples, blood draws from neonates provides a very small sample. So the mass spectrometric method is a way to deal with a very small sample size. Certain drugs may be monitored by their metabolites. Drugs with highly variable metabolism and bioavailability may require individual patient monitoring. An example would be the organ transplant rejection drug rapamycin, also known as sirolimus. Patients taking this drug routinely have their blood monitored by a liquid chromatography mass spectroscopy hyphenated assay. Environmental testing makes heavy use of mass spectroscopy for testing air, water, and soil contamination. I'm not very familiar with the use in evaluating oil composition, but I would imagine that elements like sulfur and things other than carbon would be useful in fingerprinting different types of petroleum. Widely used in forensics. When you go to the airport and your laptop is swabbed and put in a device, that is not a mass spectrometer, but it operates by a principle that is related to mass spectroscopy. If you have interest in that, we can go into that another time. But many uses of mass spectrometry, and 2-3 decades ago, a single mass spectrometer could take up an entire room and require one full-time spectroscopist and a technician to keep that operating. Now, mass spectrometers are routine laboratory instruments that sit on a benchtop and often allow for walk-up use. People that are not mass spectroscopists, that are routine practicing organic chemists. So that technology has changed quite a lot, and I think it will continue to be more and more accessible. And as demand increases, the volume of units sold increases, and that lowers the cost. And this will allow even more applications of mass spectrometry where previously it was cost prohibitive. So when we started, we talked about the molecular ion, and the molecular ion is if the radical cation that's formed from electron ionization is stable, then the molecular ion will have the mass of the parent compound. And in the case of benzene, we also see that the molecular ion is the largest peak in the spectrum. So it's arbitrarily set to 100% of the relative abundance scale. That peak is known as the base peak. The base peak. Now, the base peak is that peak that's set to 100. In this case, the molecular ion and the base peak are the same. And that's because benzene is very stable and the molecular ion peak does not easily fragment. For most compounds, the molecular ion peak is not the base peak, because for most compounds, that radical cation that's formed isn't stable and it undergoes fragmentation. So in this spectrum, we're shown the mass spectrum for pentane. And the molecular ion peak has a very low relative abundance. An abundant peak, the base peak, is at a m/z ratio of 43. So it's important to recognize that the base peak will rarely be the molecular ion peak. So something I'd like to spend a second on. We've been given the structure. So this is pentane. That's C5H12. And on a piece of scrap paper, I worked out the molecular weight is 72.15. So you can see this is 70, 71, 72. So this is the molecular ion. And you might be asking yourself, how do you recognize that that's the molecular ion and that this little peak here isn't? And as we do more examples and you practice, you will develop a sense of this, that these very small peaks here are often attributed to impurities, but in this case, this peak is related to the carbon-13 isotope. Carbon-12 is the predominant isotope of carbon. It's 99%. I think when we talked about carbon NMR, I think we covered this, that rounding to whole numbers, the ratio of carbon-12 to carbon-13 is 99 to 1. So the carbon-13 isotope, the NMR active isotope, is about 1% of the abundance of carbon-12. So we'll always see a peak, and the larger the molecule, the more visible, the larger number of carbons, the more visible the carbon isotope peak will become. But it's always going to be small relative to the carbon-12 peak. So with time, you will recognize that this is most likely the molecular ion. So let's go to the next slide. The steps in analyzing a mass spec is to identify the molecular ion peak, because this gives you your compound molar mass, your molecular weight. The m over z of the parent ion is the molar mass of the compound. There's something called the nitrogen rule, and one of the things the nitrogen rule tells us is if we have an odd numbered mass, a molecular ion peak, then this means that there's an odd number of nitrogens in the atom, that there's typically it's 1, but it could be 3, 5, 7, but it has to be an odd number of nitrogens. And from that, we also know that if we have an even massed molecular ion peak, it either means there's no nitrogen or the number of nitrogens is even. And here are some examples on the pentane structure. That with pentane, the nominal mass is 72. It's an even number. There are no nitrogens. With one nitrogen, we have an odd number of 73, and the molecular ion would be 73. If we have two nitrogens, we go back to an even number. We have a molecular ion parent ion mass of 74. Now this slide shows what I was mentioning a moment ago. This is the mass spectrum for methane, and the molecular ion peak. So carbon has a mass of 12. Each proton is a mass of 1. So that's 12 plus 4 is 16, and we see the molecular ion peak here at 16. This also happens to be the base peak. And again, we see the small peak separated by one mass unit, and that's attributed to the presence of carbon-13. So you will always see a one mass unit spread, a small peak, up to a higher end of the scale from the carbon-12 peak. And here in the case of decane, which has 10 carbons, the height of the carbon-13 isotope peak is more visible because there are more carbons. So the carbon-13 to carbon-12 isotopic ratio is one that you should remember. It's characteristic, and it's going to show up in every spectrum of our organic compounds because they are predominantly carbon. There are a few other diagnostic isotopic ratios that you should commit to memory. And one is the chlorine isotope ratio. Chlorine has two abundant isotopes. The chlorine-35 is 76%, and chlorine-37 is 24%. So compounds containing chlorine will always show a 3-to-1 ratio of their molecular ion to the corresponding ion containing the higher isotope, the chlorine-37 isotope, which is M+2, the M+2 molecular ion peak. So you see that here. The molecular ion peak, which happens to be the base peak here, is at, this is 110, 111, at 112 m over z. And then 113 is the carbon isotope peak of this peak. Then 114 is the chlorine isotope peak. So this pattern of 3-to-1 in the peaks is what's diagnostic for the presence of chlorine. And then any fragment that contains chlorine will also have this 3 to 1 ratio. A fragment, so when the molecule fragments, the portion of the molecule that does not contain chlorine will no longer show the that isotope peak. So that's a second thing to recognize and useful in trying to use the fragments to understand what the parent molecule is. And then I began showing you a spectrum of bromobenzene in the isotopic ratio for bromine. I said it's roughly 50-50. It's 51 to 49. So molecular peaks with bromine will have a strong molecular ion peak to M+2 molecular ion peak. So you'll see paired peaks separated by 2 mass units. And that's diagnostic for the presence of bromine. So this ion here, the mass ion, does not, whatever fragment is responsible for this, I said mass ion, sorry, the base peak. The ion that's responsible for the base peak does not contain bromine because there is no bromine isotope pattern for this peak. In this case, this also is not the bromine isotope pattern. The spacing is only 1 mass unit, not 2 mass units. So bromine. So this is also not from the bromine isotope pattern. And as I mentioned, often the fragmentation contains a lot of structural information. In this example, we had pentane, which is C5, and the loss of a methyl group is a mass decrease of 15 units, 12 for carbon, 13, 14, 15 for the 3 hydrogens. Sorry, I added some terms here. The CH2 group is referred to as a methylene group. So when we lose a methyl, this is 15, 12 plus 3 is 15. When we lose the methylene group, this is 12 plus 2, that's 14. So together, this is 29. So it's our molecular ion minus 29. And then an additional methylene loss is another 14. So if we see peaks that are regularly spaced that are 14 mass units apart, we can surmise that these are loss of methylene groups. So here is the spectrum of pentane again, and we see clusters around each ion. They're the result of further fragmentation, loss of hydrogen atoms. And some of those can be very difficult to interpret, but here we see that we have our molecular ion peak, and if we record the mass, this is 70, 71, 72. So 72, and then if we look at this next significant peak, this is 55, 6, 7, that's 57. And if we do the subtraction, that's loss of 15. So we can recognize that from here to here is loss of a methyl group. And then if we recognize that, we can start looking for 14 mass unit losses beneath this. So 57 minus 14 would be 43. Yeah, so that would be here. M minus 29. Oh, sorry, I jumped to. Sorry, I recognize what I did. 57 is here, and that's loss of the methyl. 40. This is loss of 43. So m minus sorry, this is a mass of 43. M minus 29 is 43. So 41, 2, 3. So this is a mass of 43. And that corresponds to loss of CH2, CH3. And then this is 25, 6, 7, 8, 9. M over Z of 29, and that would be 43 minus 14. And so on. So this regular spacing. And this is also really common in synthetic polymers like polyethylene, where you have loss of ethylene groups. So it's very characteristic of a straight chain alkane successively losing methylene groups. So looking at the fragmentation, all the fragments are possible, and most are observed, but there's still a preference for the most stable fragment, and a fragment that produces a tertiary carbocation is going to be the most stable fragment in this case. So this is 1, 2, 3, 4, 5. So this is a 2,2-dimethylpentane. The loss of the tertiary butyl group to give this tertiary carbocation is going to be very stable. So the M minus 43 peak in this example will be the most abundant. The mass spectrum of alcohols is interesting. There are two main types of fragmentation that you see for alcohol. There's the alpha cleavage and dehydration, or loss of water. In the alpha cleavage example, the radical cation that's formed, you have homolytic bond cleavage. So one electron from this carbon-carbon bond leaves with this fragment, and you have the CH2R group with the radical on it. And the radical from the radical cation that's formed together with the other electron from this homolytic bond cleavage forms an electron pair to give the double bond here and carrying the cationic charge. And then this is a resonance structure.